So if you know what y equals 1 over x looks like, and that's what it looks like, you could always use your calculator to remind yourself of the features of it. There's a horizontal and a vertical asymptote, a couple of key points, 1, comma 1, negative 1, comma negative 1. And you know what 1 over x squared looks like, a couple of key points, 1, comma 1 and negative 1, comma 1. Again, we have horizontal and vertical asymptotes on the axes. If you know what either of those graphs look like, then you should be able to transform either of those graphs. What was that?
There was a layer of ice on top of my water bottle, so I shoved my thumb in it, and now there's water.
It's like this explosion. If you take 1 over x equals y, or y equals 1 over x squared, and you transform it by applying a, h, and k, then that's what the two functions look like in terms of an equation. A, h, and k do the same things they've been doing. Nothing's changed over the past couple of weeks. The same things they've been doing for the past 3.5 months, 3 months, whatever it is, 3 months. So take a look at your work, please. Does anybody have questions? I'm sure you do, that you would like me to go over. Go ahead, Annalie. 5A. 5A? So this is one of these ones where we want to, this is interesting. We want to write this as a over x minus h plus k. And the example that I gave you, I'm going to do B first. The example that I gave you that had this as a task could have been accomplished by doing synthetic division. So if I did synthetic division of x of that x divided by x plus 8, then I have to put the negative 8 here. And I have to put a number which represents the coefficient of all of the terms of the polynomial I'm dividing by. I'm dividing into x, and that's 1x plus 0. So I do need that 0 there to make sense of this. And in B, what you would do then is you would bring the 1 down, you would multiply and get negative 8, and you would add to get negative 8. This is the quotient. And this, of course, is the remainder. The only way this becomes remotely useful is if you understand that what that means in terms of the division algorithm is that this is equal to the quotient of 1 plus the remainder over the divisor. And I was, thinking ahead here and realizing that I want to put the remainder over the divisor first, because then I can compare things to y is equal to a over x minus h plus k. So we know that the horizontal asymptote will be at y equals 1. The vertical asymptote will be at x equals negative 8. It will involve a vertical reflection and a vertical stretch that's quite severe, stretched by a factor of 8. I have never tried to do something like A with synthetic division. I don't know if it will work, because there's a simpler approach here. And it's to simply say, I'm going to review something that we talked about in the trig unit. It popped up. If I had 7 over 3 plus 1 over 3, we normally bring these together and write 7 plus 1 over 3. And you would even go further and write 8 over 3. But what that means is that when you have a monomial denominator in a fraction, you can split the fraction up. So I can write A as y is equal to 11x over x plus 12 over x. And what happens is the x in the first term cancels, and I'm left with y is equal to 12 over x plus 11. And that's equivalent to me writing 12 over x minus 0, which means that h is 0. You can see that a is 12 and k is 11. I honestly am about to try something that I've never tried before. I'm going to try to do synthetic division with that monomial denominator. I don't see any reason why mathematically it shouldn't work. I think it has to, but I've never tried it before, so I don't know. So I am dividing by, well, I'm dividing in A 11x plus 12, and I need to divide that by x. And the number that we put here is always the zero of, I want to say the zero of the binomial, but x is not a binomial, so I'm going to say the zero of the divisor. I don't know what's going to happen here because the zero of the divisor in A is 0. The divisor is x. The value of x that makes x 0 is 0. I don't know what's going to happen here. Well, let's find out. 11. 11 times 0 is 0. I add it, I get 12. So this is my quotient. This is my remainder, which means y is equal to my remainder over the divisor plus the quotient. It worked. I mean, I figured it would, but like I said, I just never tried it before. Bless you. Other questions? Go ahead. 8? All right, now we're talking. This is a Math 30-1 level problem. This would actually appear maybe as a 2-mark written response question, but it definitely could appear as a multiple choice or, depending on how it's worded, a numerical response question. The difficulty here is that you have two unknowns that you need to determine. I mean, I know that most people will look at that equation and see 4 variables. It doesn't have 4 variables. It has 2 variables, x and y, and it has 2 parameters, which are constants. And we've done many problems in the past like this, but I'm going to give you a simpler one just to begin with. If I had y equals a over x minus 1 plus 7, and I told you that this passed through the following point, and I said determine the value of a, we view this as a missing parameter, and that 2 comma 3 means that whenever you put x equals 2 into the function, you have to get a return of y of 3. So I would take this and I would apply the 3 to y, and then I would have a over 2 minus 1 plus 7. Well, that happens to be equal to 3 equals a plus 7, because 2 minus 1 is 1, and I can solve that. Okay. This is not so simple because it has 2 missing parameters, but that means we can set up 2 separate equations and solve a system of equations. So one of the points on the one hand is 10 comma 1, which means when I put 10 in for x, I have to get 1 for y. That's an equation that will have a and k in it. On the other hand, it passes through 2 comma 9, so I can get a second equation by replacing x with 2 and y with 9. Let's see what happens. I mean, I think you know what needs to be done. Now let's talk about how we're going to do it. 10 comma 1, so y is 1. And then we have a over 10 minus 7 plus k. And I'm just going to clean that up and write 1 equals a over 3 plus k. That over 3 is a bit of a problem. I can either right now or in a few minutes multiply both sides by 3 to get rid of it. We'll leave it. When I look at my second equation, so this is equation 1. When I look at my second equation, I'm going to have 9 is equal to a over 2 minus 7 plus k. And if I simplify that, I get 9 is equal to a over negative 5. I just think algebraically it makes sense to put that negative on the top. Plus k. And now I'm going to solve this system. I want to turn these two equations, they're both linear, but I want to turn them into linear equations that don't have fractions in them. So I'm going to multiply both sides of this equation by 3. And I'm going to multiply both sides of this equation by 5. And then, we're slowly working towards something that resembles a Math 10 problem, really. I'm going to get here 3 is equal to a plus 3k. So 3 times 1 is 3. 3 times a over 3, the a's cancel. Sorry, the 3's cancel, and I'm left with a, and then 3 times k. This one, 5 times 9 is 45. When I multiply 5 by, don't forget about this negative here, by the negative a over 5, I get negative a. Oh, that's really nice because I noticed the other equation has positive a, so if I were to add them, the a's would be eliminated. Plus 5k. And that's exactly what I'm going to do. I mean, I know you can't move stuff around here like that, but I'm just going to take a shortcut here. Just double check 45, negative 5, negative a, and 5k. I think it looks okay. I'm going to add these two equations. We kind of hit the mathematical jackpot here because these two terms are opposite. If they weren't, I think they have to be in this kind of question. But if they weren't, then we could multiply one equation by whatever we needed to, and maybe the other equation by whatever we needed to arrange that fortunate situation. When I add these, I get 48 equals 8k. So now I can divide both sides by 8 and get 6. Once I know what k is, I can just grab any of these two equations and was it really 3 equals a plus 3k? It was, okay. And put in for k the value of 6 that I got. That's an a, not a 9. And then solve for a, which will be 3 minus 18. So apparently a is going to be equal to negative 15. Is that right? Yeah. Is that okay? Okay. Other questions? All right, we're going to move on and look at the next lesson in this unit, which is called Analyzing Rational Functions. And, in terms of this chapter, chapter 9, this lesson is maybe the most important thing. Should you be able to transform 1 over x and 1 over x squared? Yes, but it's not the big picture here. Because not all rational functions are transformations of 1 over x or 1 over x squared. So what we're looking at doing today is analyzing rational functions of any form. Any polynomial over a polynomial is a rational function, essentially, as long as the denominator is not equal to 0, and as long as the denominator is not a degree 1 polynomial function, because then there's no variable in the denominator. So we're going to be looking at functions that are rational in any form, not just transformations of these two base functions. And then we're going to be discovering that non-permissible values in an equation, could correspond to one of two different things. They could correspond to an asymptote, and it would be a vertical asymptote, or I like the phrase point of discontinuity, but the diploma exam very often just says hole. Okay. I think this is Math 30-1. We should call it what it is. Yes, it is a hole in a graph, but it is more properly called a point of discontinuity. To begin with here, we're going to graph these two functions, but first let's write out the non-permissible values of x in f of x. Well, look, you can't divide by 0. So it's not even a matter of doing anything algebraically. I think that you should be able to say the non-permissible value of x is 2. What that means is that x is not allowed to be 2. Okay? And if you want an algebraic proof of that, the denominator cannot be equal to 0, and when you solve that little non-equation, I call it a non-equation because it doesn't have equals, it's not equal to, you'll get x is not equal to 2. And for the same reason, you're going to get the same result here. And there's nothing new there. That's not a Math 30 concept. That's just, we talk about that in a limited way in Math 20. The denominators of rational expressions cannot be 0. The difference here is the rational expression is equal to y, so we call it a rational function. Okay. Now we are asked to sketch the graphs of these using a graphing calculator. So let's take a look at the first one. And it's kind of important that you follow along here. For a number of reasons. Let me just get to it. Y is equal to, I need to put brackets around the entire numerator, and I need to put brackets around the entire denominator. If I don't, then I won't be dividing the entire quadratic by the entire linear. So it's x squared minus 8 times x plus 15, close the brackets on that, and then I divide by, in brackets, x minus 2. Just take a look to make sure that you've entered everything correctly, and I have not. There we go, divided by bracket x minus 2. Let's see, x squared minus 8x plus 15 over x minus 2. Let's use our old friend Zoom Standard, which is Zoom 6, to take a look at what this thing looks like. That somewhat vertical line in the center of my graph is just my calculator trying to cope with how to connect those two parts of the graph. There's actually a vertical asymptote there, and we already know that because when we compare this graph to our statement about the non-permissible value, x cannot equal 2. And one of the things you'll see, I'm going to change my window settings slightly. Well, I guess I should talk about how I'm changing them. There is all this space over here that is wasted. I don't really care about that. When I go Zoom Standard, it scales it from -10 to 10. I don't care about a lot of that, so I'm going to change the window setting maybe -6 to 10 for x. The other thing is I can see a lot of stuff here, but over here I'm missing out on some things. Like maybe I want to see what's happening a little bit lower. So again, when I go Zoom Standard, this is -10, this is 10. Maybe I should look for y down to -15 or -18. This is kind of the process that's going on in my head when I go to window and I go, well, let's go from -6 to 10. And instead of -10 to 10, let's go -18 to 10. Doesn't really matter. But now I can get a better picture. And in fact, I lucked out. I don't actually see that jagged line. Don't think your calculator, if it draws that jagged line, is trying to tell you there's an asymptote there. Your calculator is just drawing it because it doesn't know what to do. So this is what it looks like. If we want to sketch this, we know that there will be an asymptote. It's a vertical asymptote at x equals 2. And then we also have a curve that looks something like this. Just give me a second here. It looks something like this here and something like this here. That's what it looks like. We didn't talk about this yesterday, but this shape you get for many rational functions, like the shape you get for 1 over x, that shape is called a hyperbola. So there's an asymptote there, a vertical asymptote. Well, let's graph the next one. And the next one is basically the same type of function. It's got a quadratic on the top, and it's on a linear on the bottom. So in brackets, x squared minus 3x plus 2, end bracket, divided by bracket x minus 2. And again, I would like you to go Zoom Standard. I guess I should just double check to make sure I've entered it correctly, as should you on an exam. Looks okay, zoom standard. And I get what appears to be a line. But this is not a linear function. I will tell you that that line you're seeing, and it's not actually a line, but let's just imagine it is for a second, is perfectly straight. It is perfectly straight. But it's not a linear function. Now, here's the problem. What does it look like when we graph it? Well, x is not allowed to be 2, right? If I go trace 1, and I could do this by going into my table and entering an x value of 1 and reading the y coordinate, I have y equals 0. If I go trace 3, I have y equals 2. If I go trace 1.95, I get a y coordinate. Don't worry about the connection between these numbers. That's not important. But if I go trace 2, I don't get a y coordinate, which means there's a hole in the graph. There's a point of what we call discontinuity. And the weird thing to try to wrap your head around, if you're really interested in this, is the size of the hole is infinitely small. Like, we're going to draw it like this, but it's infinitely small. Because I can go trace 1.99999. I can go trace 2.00001. I'm allowed to put in any value of x I want, as close to 2 as I want, but I can't put 2 in. Now, you can actually see the hole in this example, but not always, if you go zoom decimal. And it's really not important that you remember this. I'm just pointing out to you, and it's not important that you understand why this happens, that when you go zoom decimal, very often you will see the break. And that hole is drawn way bigger than it really is, right? But how do we draw this? How do we sketch this? Well, it is a straight line. Just hold off on sketching anything for a second. But there is a hole over here at x equals 2. And this line does go on in both directions. At an earlier grade, I would make a big deal of, make sure you put arrowheads on the end, but we know that it continues in both directions. So two functions, they both have a quotient that contains x minus 2 as a factor. They both have non-permissible values of 2, but the meaning of the two is different. And one of the goals in this lesson is you should be able to look now, once I show you how, you should be able to look at this function and say, oh, this is going to be a vertical asymptote, but when you look carefully at this function, you should be able to say, no, it's a hole, without looking at the graph. There's something about the functions. And that's the next part. Describe the difference between the two graphs in terms of the non-permissible values. F of x, where x cannot equal 2, has a vertical asymptote at x equals 2. That was the one that had the asymptote, wasn't it? F of x? Okay. G of x, did I call the other one g of x? I did. G of x, again, where x is not allowed to be 2, has a point of discontinuity, or hole, at, wait a minute though, a point cannot be described by one number. A point has an x and a y coordinate. All we know right now is the x coordinate is 2. We don't really know the y coordinate, although I suspect maybe some of you do. If I go back to my calculator and I go trace 1.9, I get 0.9 for y. If I go trace 1.95, I get 0.95. If I go trace 1.99999, whatever, I get a number, and this number that I'm getting keeps getting closer to 1. So we would suspect that the y-coordinate there is 1, and we would be right. Okay? And we can put that in, but I'm going to explain to you in a bit how to find it algebraically. Any questions about the two different types of non-permissible values in terms of how they reveal themselves on the graph? All right. So, how would we know which is which? Well, look what it says here. Simplify each function. In Math 20, you're taught that rational expressions are simplified by factoring first. If you had me for Math 20, and we started that unit on rational expressions and equations, the very first thing you saw when we started was a big word that said factor. Doesn't matter whether you're solving an equation, whether you're simplifying a rational function, whether you're multiplying them, dividing them, adding them, factor. So we have to factor everything here first. And the numerator of this is a trinomial that's quadratic. Look how I wrote x minus 2. I wrote it in a set of brackets because it's a factor. Are there two numbers that multiply to give negative 15 and add to give negative 8? Positive 15 and add to give negative 8. It'd be negative 5 and negative 3. Okay. So x minus 5, x minus 3. G of x, same kind of deal. Are there two numbers that multiply, sorry, I'm getting ahead of myself. Grace, are there two numbers that multiply to give 2 and add to give negative 3? Good. Negative 1, negative 2, negative 2, negative 1, whatever order we want. See, here's the rule that we're going to learn. If that factor, which produces the non-permissible value that you're not allowed to use, cancels, then it's going to be a whole. But before we formalize that, if I write g of x is equal to x minus 1, I have a fairly high-level, conceptually challenging question for you. If g of x is equal to this, why is this an incorrect statement? Why am I not allowed to say g of x equals x minus 1? Yeah, Jack.
Because you forgot to include the non-permissible values.
Right, and that's something in Math 20 I think you might be remembering from there. And it may have come up elsewhere, I'm struggling here, maybe not though, in this course. The bottom line is if you have a non-permissible value of the function, no matter how you rewrite it, that non-permissible value is tattooed to the function. It stays with the function everywhere. So this is x is not equal to 2. Well, guess what y equals 1 over x looks like? Y equals 1 over x looks like that line. That's why it appears linear, because when we cancel that factor, all we're left with is a linear expression. But the rational part of it says, no, we have a non-permissible value at 2, comma 1. And I haven't explained to you how we can get the 1 yet. Okay? But I'm about to. If the factor which is responsible for the non-permissible value of x does not cancel, then you're going to see a vertical asymptote at that point. That's what it boils down to. So what are the domain and range of each function? Well, the domain for each one is that x is not equal to 2. I can't remember if I omitted the range for f from your handout or not. Just put omit there. I don't want to go down a rabbit hole of talking about the range here because it's not important. What is the range of g of x, though? What is the range of g of x?
Y cannot equal 1.
Right. So if that whole is at 2 comma 1, 2 is an x coordinate, 1 is a y coordinate, when we say x can't equal 2, that means y can't equal 1. X and y are not allowed to be the respective values of the coordinates in the whole. So y is not allowed to be 1. Does anybody know or suspect, and you don't have to turn back, I'm just going to refer to this. You can go ahead and turn the page if you want to. Can anybody tell me how you could find out that the y coordinate that's not allowed to exist is 1? Right. See, you're not allowed to put 2 in for x though, right? But once you eliminate that factor, mathematically it's possible to put 2 in. So what you will be finding by putting in the value of x2 that doesn't exist is the value of y that doesn't exist. So if you were to put the non-permissible value for x into whatever remains, you're going to get the non-permissible value for y. If you put in 2 for x, you'll have 2 minus 1, which is 1. Just to show you the graphs in more detail, no, I'm not going to bother. Describe the behavior of the graph near each non-permissible value. And now I realize why I had the graphs. I'm going to put this one first. When I say what is the behavior of the graph near the non-permissible value, what I am asking is this. As x gets closer to the value that it's not allowed to be, what does y get closer to? As x gets closer to the value that it can't reach, what does y get closer to? So let's take a look at g of x first, which is this graph. And I already kind of demonstrated this to you on my calculator by going trace 1.9, trace 1.99, trace 1.999. As x gets closer to 2, what is y getting closer to? 1. Whoops. Now let's take a look at the second graph. I have to graph it in 2 places. This is the vertical asymptote. Just a little detour, just pull off the road for a second. Those of you taking calculus, it turns out there's a slant asymptote as well. There's something else going on. We would never talk about a slant asymptote formally in this class, but some of you will take calculus either this year or next year. There it is. So as x on this graph gets closer and closer and closer to 2 from either side, what does y get closer to? Annalee?
Infinity and negative.
Right, plus or minus infinity. And I'm just going to write it as plus or minus infinity. Because it may be that the graph on both sides goes up to infinity, or the graph on both sides goes down to infinity, or the left side goes up and the right side goes down. When I say down to infinity, I mean down to negative infinity, or the other way around. It isn't always what this looks like. We just say in general plus or minus infinity. All right, example 2. What are the non-permissible values of all of these functions? So what you need to do is say to yourself, what are the solutions to this statement? And there aren't any solutions to that statement. The denominator can't equal 0, but if you try to rearrange that for x, you would subtract 4 from both sides. One way to do it, you would subtract 4 from both sides and get x squared equals negative 4. Well, you can't take the square root of negative. This tells us there are no non-permissible values of x. The domain of this function will be any real number. And we're not going to graph these, but you might be interested to know what it looks like. You can graph it later on your own. To find the non-permissible values here, you're going to solve this statement. I would say at some point you should be able to just look at that and go plus or minus 2. You can move the 4 over and take plus or minus the square root, or you could factor it as a difference of squares and just see that each factor cannot equal 0. Very basic factoring. Here, x minus 4 cannot equal to 0, which means x cannot equal to 4. Here, the denominator is x plus 2, which cannot equal to 0, which means x cannot equal to negative 2. Are we okay with those statements? Like, I'm asking you to check my work and think about it yourself as well. Okay. So, that's the first part. Second part. With the ones that have non-permissible values, and I'm going to add something else up here. I just keep showing the equations again and again so I can refer to them up here. Here, we said there were no NPVs. They didn't exist. Here, we said x is not equal to 2 or negative 2. Here, we said x is not equal to 4. And here, we said x is not equal to negative 2. Am I right? That's what we wrote down. Okay. You'll notice that what I did is I factored everything, and you should factor everything right now as well. If I factor x squared plus 2x, I can factor a common factor of x out. So the top or numerator of this rational expression becomes x times x plus 2. We already know what the bottom of g of x is factored because we factored it to solve for the non-permissible values. The bottom is x plus 2 over x minus 2, or sorry, the bottom is x plus 2 times x minus 2. And the numerator, again, we can factor an x out. With h of x, we can factor an x out of the numerator and be left with x plus 2. The denominator is a binomial that's linear, so it's non-factorable. Nothing you can do with it. And then the last one, the same thing. So, there are no holes or vertical asymptotes for f of x because there are no non-permissible values. G of x will have a hole at a particular value of x, and it will have a vertical asymptote at a particular value of x. And I wrote those differently because the whole is going to be two numbers. Which of these numbers, positive 2 or negative 2, is the x-coordinate of the whole? Leighton, want to give it a crack? So what I'm getting at here is it will either be this or it will be that. And you should be able to figure out that it's one of each, but I told you it's one of each. My question is, which value of x that's non-permissible is the x-coordinate of the whole? Without graphing it. Because if you don't know the answer to that, you missed the whole point of this. If the factor cancels, the 0 of the factor goes with the whole. If the factor doesn't cancel, the 0 or non-permissible value is a vertical asymptote. So since in g of x, the x plus 2 will cancel, whatever non-permissible value x plus 2 creates, that will be associated with the whole. And I don't know how you're going to remember that. It just occurred to me that if it cancels, it goes away. It's not there. It's like a hole. I don't know if you want to try to remember that. So the whole will be at negative 2 comma something. And we'll come back to that. The vertical asymptote will be at x equals 2. This non-permissible value in h of x is not equal to 4. Is that going to be associated with a vertical asymptote or with a hole? McKenna, what do you think? Right, because that factor survives. It doesn't cancel. And again, I know I risk being repetitive, but if the factor cancels, you get a hole. If the factor doesn't, you get a vertical asymptote. We need to know these things. So we're going to have a vertical asymptote. I'm tired of writing out the word asymptote, so I'm going to abbreviate it at x equals 4. And what about here for x is not equal to negative 2? Will that be, Kendra, will the negative 2 for k of x be at a hole or an asymptote? Right, because it comes from the x plus 2, which cancels. So you get a hole at negative 2 comma something. And we'll come back to that. The next part is, if there's a vertical asymptote, write the equation of the asymptote. Well, I already did, didn't I? And we already did. Whether you wrote this under B or you want to rewrite it under C, it doesn't matter. I guess maybe I should reorganize my notes. I just find repeating the equations over and over again up here is easier for me. So if you tend to do all of the work in one section, that's fine. So we've done that. Just to be clear, a vertical asymptote will exist at x equals 2 here and at x equals 4 here. For those with a hole or a point of discontinuity, what are the coordinates? Well, we knew the hole was at negative 2 comma something here. Correct me if I'm wrong. And the hole for this one was at negative 2 comma something as well. Correct? How do we find the y coordinate? What we do is we cancel the factor that prevents us putting in the x value that we're not allowed to use and say to ourselves, that's an x value that never exists on the function. So if I put that into whatever else remains, even though it's still a non-permissible value, I will get the y coordinate. So you have to put negative 2 in for x in x over x minus 2, and I'm going to get negative 2 over negative 4, which is 1/2, I believe. Same thing here. Well, this is even easier because the x plus 2's cancel. All you're left with is x. So when I put in the value of x that doesn't exist because it's an x coordinate of something that's not there, called a hole, I will get the y coordinate that doesn't exist, which will be the y coordinate of the hole, and it will be negative 2. Capiche? Any questions with that? All right, match the following graphs. So in order for you to analyze rational functions, you want everything to be factored. So when I factor this, I get x times x plus 2 over x plus 2, x minus 2. I hope you can see, that might even be one of the functions that we just analyzed. I hope you can see that one of those non-permissible value factors cancel and the other one doesn't, which means there will be a hole and a vertical asymptote. It must be graph 1. This is a of x. And by the way, looking up here, there will be a hole at negative 2. Whoops, my mistake. It must be graph 2. Looking up here, since the x plus 2's cancel, there will be a hole at negative 2. Since the x minus 2 survives, there will be a vertical asymptote at 2. This, we can factor a 2 out and be left with x plus 2. But since the denominator is a non-factorable quadratic, and it even goes further than that. Since you cannot find a value for x that makes that 0, because if you put x squared plus 1 equal to 0 and tried to solve it, you'd end up taking the square root of a negative. The denominator of b can never be 0. It's not even possible, which means it's going to be the graph that has no holes and no asymptotes. And by a process of elimination, this must be c. Of course, this is 2x over x plus 2x minus 2. Two non-permissible values, negative 2 and 2. Nothing cancels, so there's 2 vertical asymptotes. Don't worry about the shape of graph 3. It's not something you need to know. These rational functions, particularly if there are no non-permissible values, can look quite weird. This isn't like polynomial functions where you're going to recognize a pattern. Does anybody have any questions about example 3? Danielle, are you wondering something, or?
So the reason that b of x is graph 3 is because x squared plus 1 isn't factorable?
I'm going to explain that in more detail. It is true that it's non-factorable, but that's not why. It's that this has no solution. If this were, if you tried to solve this using the quadratic formula, like imagine this is equals, not equal to, you would have negative b, which is nothing, plus or minus the square root of b squared minus 4ac over 2a, which would be 2. But if you calculate b squared minus 4ac, you're going to get negative 4. Just trust me on that. You cannot take the square root of a negative. If you tried to solve this statement, I resist calling it an equation because of the not equal to. You could do this. But you still encounter taking the square root of a negative. So when I said, and I corrected myself, but I don't think I was clear in my correction. When I said there are no non-permissible values because it's not factorable, that's not the reason. The reason is there are no values of x that can ever make it 0. It's not possible. Because if you had a denominator of that denominator is not factorable, but there are non-permissible values of plus or minus root 3. Because if I say, what's the solution to this statement? I get something that I can take the square root of. Have I alleviated any confusion? Okay. All right, let's take a look at another similar example. Well, this is just a little bit of practice with factoring. X squared plus 2. I'm not saying you should be able to factor that quickly, but pretty darn close. We can't be whittling away 4 or 5 minutes on an exam trying to figure out how to factor some very basic quadratics. So in graph k of x has 2 non-permissible values, but none of the factors that produce the non-permissible values cancel, which means it has 2 asymptotes. This has to be k of x. Again, don't worry about why it looks like what it looks like. It just does. You could make a table of values or graph it on your calculator. Since L of x has 2 non-permissible values, but one of the factors for the non-permissible value cancels, it will have a hole at that 0 of 1. Well, there's a hole on graph 1 at x equals 1. And at x equals negative 1, which comes about from that factor, we will have a vertical asymptote, which means that this is L of x. Which means that this is m of x. But, does this factor on the bottom cancel? Well, it has to because there's a hole. My question now is, how does that 3 minus x cancel? You remember, Caden? Perfect. You recognize that I'm missing my y here, but we're talking about something else. And I don't want to put words in your mouth, but I think you mean factor a negative 1 out of the bottom. Yeah. So when I factor a negative 1 out of positive 3, it becomes negative 3. And when I factor a negative 1 out of negative x, it becomes positive x. So those cancel. And I'm left with x minus 2 over negative 1. I think you know this about me and negatives. I don't like a negative in the denominator. So probably what I would just do is write y equals negative 1, x minus 2. And you could certainly multiply that negative 1 through. But there's a shortcut. You can either remember to do that when you see this, or anytime you have this over this, it will be equal to negative 1. Take 10 minus 7 divided by 7 minus 10. You get 3 divided by negative 3. You'll get negative 1. So there's a kind of a pattern here you can recognize. When you see that, you can cancel. Anyway, that's why we get a hole. You can cancel as long as you put a negative. One last thing. This is the only other thing, and this example is going to teach you one final thing. What we want to do is determine the equation of this rational function. And unless you're told it's a transformation of 1 over x or a transformation of 1 over x squared, stay away from the AHK thing. Okay? Well, we're going to build this from the ground up and say y is equal to, and I'm looking at this and seeing that there's a non-permissible value of negative 2. Which means x can't equal negative 2. That must mean there's a factor of x plus 2 in the denominator of this function. I see there is a hole at x equals 3, which means there's a non-permissible value of x at 3, so x is not allowed to be 3. The only way that makes sense is if there's an x minus 3 in the denominator. Why do I know there is also an x minus 3 in the numerator? Grace?
Because they have to cancel in order for it to make a hole.
Right. The factor that produces the hole has to cancel with an identical factor on the top. But I will tell you what, right now, if you were to graph this, it doesn't look like that. I'll show it to you. There's something else that you don't know yet, but let me go ahead and graph this. And this is a good exercise in how to enter this. I can go x minus 3 divided by, if I do this, I will have entered it wrong because that's only going to divide by the x plus 2. I need to put another set of brackets when I enter this here. Or FOIL it out and put one set of brackets, but that's a waste of time. So I've got x minus 3 over x plus 2 times x minus 3. I am going to manually set up my window setting to match this grid. This goes from negative 10 to 6. And it goes from negative 11 to 6, but you get the idea. And it goes from about negative 10 vertically to 10 horizontally. Not even close. I mean, if I go, what's the y-intercept? I go trace 0. The y-intercept of this is only 0.5. The y-intercept of that's supposed to be 2. Now, you're not going to figure it out through stretches or anything else. Does anybody have an idea here? And I will give you a hint. We need one more factor on the top that is not related to the non-permissible values. Kendra, do you know?
Find out what happened to the original points of 1, 1, and negative 1, negative 1.
If you do that, you're wading into quicksand, mathematically speaking. And that's why I said, so the comment was, well, why don't we go with that key point of 1, 1 and see where that lands. It won't work when we have holes and asymptotes combined together. So stay away from stretches and shifts, A, H, and K, unless you're guided in that direction. There's bound to be an exception, but it's not going to work here. I'm going to write in the other factor, and I want to see if you can figure out why I need this factor. There's an x-intercept of negative 4. The only way you get an x-intercept, don't erase this. The only way you get an x-intercept is if y is 0, right? How can y be 0? Well, y is a fraction. The only way a fraction can be 0 is if the top is 0. And that means when we put in negative 4, we have to get 0 on the top because it's an x-intercept. So we have another rule now. The other rule is an x-intercept is represented by a factor in the numerator. And that's what this lesson boils down to. Factor in the denominator means non-permissible value. If the factor in the denominator cancels with an identical factor in the top, then you're talking about a hole. If the non-permissible value in the denominator does not cancel, then you're talking about a vertical asymptote. If you have a numerator factor that does not cancel, like x plus 4, it corresponds to an x-intercept. And that's what we mean when we say analyzing rational functions. That's what's involved. One final comment. Is this class end at about 1:55? Okay. One final comment. If I had this, I hope everybody would agree there's a hole at 1, at x equals 1. And the y coordinate would be whatever we get when we put 1 elsewhere. What about still non-permissible? I've got x minus 1 in the denominator. Will it be a hole? I guess we could graph it. What's your thinking here? It's going to be an asymptote because only one of them cancels? Let's see if that is true. I am going to, when I enter this, I'm going to enter it as x squared plus x minus 2, so I don't have as many brackets. I guess it doesn't really matter. On the bottom, I have x plus 3, and then I have x minus 1 squared. By the way, if you want to truly see what a rational function looks like, you have to graph it without canceling anything. Right? I have x squared plus x minus 2. That I just foiled at the top. I don't know why I decided to do that. I think it looks okay. Zoom 6. Well, x equals 1, Oh, did I? Oh, then this is a polynomial function, of course. Look at that. Thank you, Jack. I was really confused there. I was wondering if I understood the math or not. You get an asymptote there. Would you agree? Okay, I'm just going to leave that. Was it x plus 3? So you get a vertical asymptote. What about if we had this? I'll just go along with the same one. So vertical asymptote. What if we had x plus 2? Jack?
There would be a point of discontinuity at x equals 1, but it would also be an x-intercept if it was allowed.
And it's not. I like that you said that, because what Jack is saying is we cancel and we're left with x minus 1 in the numerator, and I just told you that would mean an x-intercept. So you want to kind of have it both ways and say there would be a hole because it cancels, but because it survives on the top, it's an x-intercept. If there's a hole, there's a hole. So what happens is you get a hole on the x-axis. All right? So page 451, 1 through 10, I'm just going to put this up here so you can take a look at, this is just a summary. You can take a picture of it if you want. You can write it down if you want. Factors in the denominator are non-permissible values. If you can cancel, it's a hole. If you can't cancel, it's a vertical asymptote. And if you have a factor in the numerator, it's an x-intercept.